Okay. Hello, everyone. Yeah. First of all, thanks to the organizers for putting together such a nice workshop. I will talk about high temperature effects in the cosmic gravitational microwave background, and this work is based on two papers. One is together with Andreas Ringwald and Carlos Tamarit, and the other one is together with Jacopo Giglieri and Enrico Speranza. Okay, so let's get started. Is there an echo? Sorry. I don't know. Okay. Okay, let's get started. I want to tell you in a nutshell how the cosmic gravitational microwave is generated. And for this, I'm showing this sketch of how we think our early universe looked like. So the highest energy scale is here on the left, so the Planck scale, around 10 to the 19 GeV. And if you go to the right on this plot, you go to lower temperatures or to later times. And so all we need is, so we know that our universe was radiation dominated at some point. And the maximum temperature, which is here, is basically the temperature that the thermal plasma had at the beginning of the radiation-dominated phase. And the thermal plasma here is depicted by these colored dots, which should depict different particle species in your thermal plasma. Okay, so this Tmax is an unknown parameter, so we don't know like how large or how small Tmax is. But in inflationary scenarios, this Tmax can go up to 10 to the 17 or 10 to the 16 GeV. If you want to have it at higher temperatures, closer to the Planck scale, you would require non-inflationary scenarios. So the lower bound for Tmax is in principle just above BBN, but you can argue that Tmax should be above the electroweak phase transition. Okay, good. So how are the gravitation waves produced? So the gravitation waves are coming from thermal fluctuations in your plasma. So in your plasma, all the particles have momentum of the temperature, and so they can collide and produce a gravitational wave. And of course, the gravitation waves that are produced from one single collision are very small because it's suppressed by 1/m Planck squared. But since this production happens throughout the whole radiation-dominated phase of the universe, you get kind of like an enhancement. You produce it for a very long time. Okay. So the main point is that because you're in the radiation-dominated phase, you kind of redshift the gravitation waves that are produced at different temperatures or different times. You redshift this to more or less the same frequency today. So this is written here. So here's the frequency today, and here's the redshift. So the gravitation waves of momenta k, you divide this by the temperature where it's produced, and here you have the temperature today. And these functions here are basically the relativistic degrees of freedoms evaluated today and at the temperature of production. So these kind of things here are on the order of 1, and what you see then, the temperature today is basically determined by the frequency today is determined by the temperature today. So, and this is basically in the gigahertz regime, in the microwave regime. And that's why we dubbed this the cosmic gravitational microwave background. So it's a guaranteed gravitational wave spectrum that is there, it's there because we know that our universe was radiation dominated at some point. Okay, so this was in a nutshell how the gravitation waves are produced. So let me now describe how you would really calculate the spectrum. And so I will do this like first in a toy model, where you just have scalars in your plasma. And then in the second part of the talk, I will do it for the standard model. Okay, so here's the toy model. We just assume you have a scalar. Oh, let's go back. You have a scalar. Oh, no. You have a scalar, and you have a quartic interaction, and you have the Einstein-Hilbert term here. Okay. So how do you describe a plasma with a scalar? So you have a distribution function, f phi, and you have a distribution function, fh. And these distribution functions, they fulfill evolution equations. So here you have the time derivative, and these evolution equations are sourced by gain term, g, and loss term, l. Okay, so let's focus on the gain term for the gravitons. So here, in the gain term for the gravitons, you have to sum over all processes which have at least one graviton in the final state. So that's the sum, and then you have to calculate the matrix element squared for the process, and you have to weight it with the distribution functions accordingly. Okay, but as you see it here, in full generality, solving the system is very difficult, because here you have time derivatives, and the functions that you want to determine, basically the distribution functions, they appear under this phase space integral, so it's very complicated to solve this. in our scenario, we don't have to solve this in full generality. We can solve this perturbatively. So what we do is we say the phi distribution function is basically Bose-Einstein distribution to zeroth order, because the phi's are in thermal equilibrium. And the graviton distribution function is basically 0, because at the beginning you don't have any gravitons. So what you do, you plug in your zeroth order solution into the equations on the previous slide, and then you obtain these higher order corrections, which are here. So let me go through these higher order corrections now. So the first one here in blue, this is coming from single graviton production processes. So you see, for example, 2 diagrams here, and the matrix element is on the order of lambda squared 1 over m Planck squared. And later you will see that the dimensionless coupling here is basically T max over m Planck. And so this also explains the naming convention here. So the 2 stands for lambda squared and T max over m Planck squared. So these are the 2 expansion parameters that we have here. All right. So the second contribution here is coming from graviton pair production processes. And the matrix element is on the order of 1 over m Planck, or T max over m Planck to the power of 4. Hence the naming convention here. So these are the lowest order contributions. They are on the order of 4. So this is obvious here. 2 plus 2 is 4 basically, and 0 plus 4 is also 4. Okay. So but then we also comment on higher order effects here. So these are then quantum gravity effects. So for example, diagrams like these would have, like, when you calculate the matrix element squared, these 2 diagrams would interfere and would lead to a matrix element squared on the order of lambda squared T max over m Planck to the power of 4. And why I'm saying what do I mean with quantum gravity effects here? I mean basically that you have virtual gravitons that show up in your diagrams. So this is what I mean with quantum gravity effects here. Okay, so there might be other quantum gravity effects, which I haven't explained here. But these would come, for example, from modifying the evolution equations and so on. But, yeah. All right. Okay, so now I want to show you the gravitational wave spectrum here, omega GW. So it scales linearly with the maximum temperature. You have a Bose-Einstein distribution, which gives you the unique shape of your spectrum. And then you have the contributions from single graviton production, graviton pair production, and quantum gravity effects. So we haven't, so first I should say these psi functions here, here, and here, they encode all the microscopic particle physics. So you get these psi functions by calculating the matrix element squareds, and then you have to perform the phase space integrals. Okay, but let's, for a moment, let's say these psi functions are all on the same order of magnitude, and then let's discuss what kind of contributions dominate. So for example, when you have very high temperatures, and that's the main topic of this talk, when the temperature is higher, when the temperature in units of m Planck is higher than the coupling in your heat bath, then these graviton pair production processes would dominate. And if that's not the case, then the single graviton production processes dominate. These quantum gravity effects here, they are always smaller than these 2 leading order contributions, because this, for example, this is on the order of lambda squared, T max over m Planck squared, so it's always smaller than the first 2 terms. So these quantum gravity effects would show up as small corrections to your gravitational wave spectrum. Good. So for example, let's say T max over m Planck is 10 to the minus 3. So that's the value that's compatible with inflation. So then this term here would be 6 orders of magnitude smaller than the term that's coming from single graviton production. So the quantum gravity effect would be on the order of 10 to the minus 6 in the gravitational wave spectrum. Okay, so good. Let's focus now on this plot here. So you see the frequency, and you see the peak. It peaks at 100 gigahertz in the microwave regime. And we choose a maximum temperature of 10 to the minus 3, a coupling of 10 to the minus 1. And in this scenario, you see that single graviton production processes dominate completely. When you increase the temperature a bit by 1 order of magnitude, you see that at some point, graviton pair production processes dominate, and the total spectrum, which is shown in black, gets this particular shape. Okay, good. So you can also derive like in an equation when graviton pair production processes will dominate. In our toy model, we find that that's 10 times T max over m Planck has to be larger than the coupling in your heat bath. There's another condition that you have to fulfill. So your heat bath always has to be in thermal equilibrium, and this is possible when Hubble is smaller than the production rate of the phis, and this leads to lambda squared larger than Tmax over m Planck. So you see the region, the red region is here, and the blue region is here, and they overlap here. So in this regime, graviton pair production processes dominate, and in this regime, single graviton production processes dominate. All right. So, but this is
you have 2 minutes left.
Sorry.
2 minutes.
Okay. But this condition here is specifically for our toy model. So let's also discuss what happens in the standard model when you have basically standard model plus gravity. So in principle, the calculation is the same. You just have to calculate more diagrams. And this has only been done for single graviton production diagrams. The diagrams for graviton pair production processes have not been calculated. I just want to tell you what you could get. So the condition for graviton pair production processes to dominate would be something like this. So x is unknown. This has still to be calculated. Times Tmax over m Planck has to be larger than the couplings. And these are the couplings in the standard model, G1, G2, G3. And you see that they approach at these ultra-high energies 0.5 approximately. So if x would be on the order of 1, then this would only dominate or play a role if Tmax over m Planck is very, very close to 0.5, so to speak. But if x would be on the order of 10 or 100, then you would lower your maximum temperature where graviton pair productions become dominant. Okay, good. So I'm showing you, that's my last slide. So that's the spectrum that contains only single graviton production processes in the standard model. And one important feature is that the peak frequency here scales with 1 over the effective degrees of freedom at the maximum temperature to the power of 1/3. And so this is kind of nice to distinguish different particle physics models at ultra-high temperatures, because this G star function is 106 in the standard model. And if you, for example, have the minimal supersymmetric standard model at these ultra-high temperatures, then the peak would shift to slightly lower frequencies. So you could really distinguish standard model and beyond the standard model theories by determining the peak frequency. Okay, because I'm running out of time, that's my conclusion. Yeah, thanks for your attention.
Yes.
Nice, thank you. So have you tried to compare with the type of spectrum that we produce from preheating?
Yeah, I mean, this mostly peaks at lower frequencies, like at megahertz or...
Similar. No. Preheating typically would peak around tens of gigahertz. So it's very much in the same ballpark.
Okay. I thought it peaks at lower frequencies. But no. Yeah, we can... I would be very interested in seeing this paper.
Actually, not difficult here. If you go to the first few slides, if you look at the Boltzmann distribution, you're assuming thermal distributions.
Right.
In the case of preheating, you would have high occupation numbers. Yeah. You just substitute those distributions for the ones you need to compute the cross sections.
Well, just comment. So we have done it for certain models where you can calculate everything. So like the SMASH model, and it's peaked. So of course, I mean, you get the highest peak from preheating, but it still is. You still see the feature from the reheating for that. So I mean, it depends. And for example, in Higgs inflation, you would also get something similar. Yeah. So in Higgs inflation, you could have even higher reheating temperature.
True. Higgs inflation is particularly efficient.
So of course, I mean, it would be nice to see the whole spectrum, but of course we are still below NF. But
maybe we can postpone the discussion to the day.
Can I just ask an immediate? Sure. I think we have a bit of time, right? We're not in a huge rush, right? But just because, and I'm not saying that just because I want to ask a question. Well, maybe yes, right? But abusing my power here. No, well, my question is that, so you distinguish between what you called quantum gravity effects, right? Which had a virtual graviton line, and then the rest, right? Which you call kind of graviton production. So if you use the language graviton production, to me, you're assuming quantum gravity, right? Because graviton to me is a word that indicates you're looking really at a quantized particle. Yeah. So would this also work with just a classical process? Like, do you require gravity to be quantized to get the spectrum?
No, I would say no, because it's like it's like the leading order processes. It's just a tree-level diagram. So I think
I'm just asking because I guess so exactly. So we're just talking about this leading order term, right? So can you formulate that completely classically without having to revert back to gravitons?
Okay, so I think what you have to do in the end is you have to keep all h bars, and then send h bar to 0. What remains is your classical result, and what it vanishes is the quantum gravity part. I think that's the way how to do it, but this might be like complicated because a loop expansion is not necessarily like equivalent to an h bar expansion, for example. But we're working on this, but it's like, yeah, so right now, like what I mean with quantum gravity is just, there's like a virtual graviton, and yeah, there might be then quantum gravity effects due to these virtual gravitons. Yeah.
Maybe,
can you not compute the fluctuations in the thermal plasma and then just use the classical source for gravitational waves? And then you never have to resort to the quantum description of gravity.
That's what you do in preheating.
Yeah. I thought this was the part of the computation that Jacopo and Mikko did many years ago.
Here we assume that the plasma is homogeneous. So it's like there are maybe inhomogeneities due to particle collisions, but like overall it's homogeneous. So I don't know what you mean with...
But your whole source is the inhomogeneous part of the plasma. I mean, you just model it as individual particles. Right. Okay, maybe this is the most efficient way of doing it. That's fine.
Yeah. So let's move on to the next talk. And we can continue the question answer in the session.